4-7, arithmetic sequences. So our objective for this section is to identify and extend patterns in sequences and to represent arithmetic sequences using function notation. So our essential understanding is that when you can identify a pattern in a sequence, you can use it to extend the sequence. You can also model some sequences with a function rule that you can use to find any term of the sequence. Okay, so before we start, let's get a couple of definitions. A sequence is just an ordered list of numbers that often form a pattern. And each number in this list is called a term in the sequence. And once we find the pattern, we can figure out what the next terms or the next few terms of each sequence are. So first problem is to describe a pattern in each sequence, and then what are the next two terms? Well, if I look at the first one, I got to figure out how I'm getting from 5 to 8, and if that works to get to 11 and to 14. Well, to get to 5 to 8, right, I'm just adding 3. And then plus 3 again, and plus 3. So to get from each of the next two terms, we are adding 3. So very simply, to get the next two terms in the sequence, we add 3 to 14. So we get 17 and then 20. Okay. So for the next sequence, well, when I look at this, I can say, well, that is plus 2.5. And then, well, that's plus 5. That's plus 10. So that didn't work. Addition didn't work. All right, so I have to look at this from another, I have to come up with another idea for how to get the next term in the sequence. And I notice that each one is multiplied by 2. So to get from one to the other, we times by 2. Okay, so the next two terms are going to be 40 and 80. Okay. Let's look at some guided problems. Same thing. Describe a pattern in each sequence, and what are the next two terms in this sequence? All right, so looking at the first one, we have 5, 11, 17, 23. So each one there is plus 6. So the next two are going to be 29 and 35. For B, 400 to 200, that's minus 200, but now we have minus 100, then minus 50. Okay, so it's not working with subtraction. So you're going to have to use multiplication or division, right? And we can say we can multiply by 1/2 to get to the next one, or if you want to, divide by 2. Okay, so the next two ones are going to be 25 and then 25 divided by 2, or 12.5. Either way, doesn't matter. When we look at these two, or when we look at these, this function right here, we notice that it's switching from positive to negative to positive to negative. That is a big indication that we're multiplying by something. Because if we're just subtracting, the answer would stay negative. Okay, and we can see that this is going to be times -2 for each one. So this would be a positive 32 and then a negative 64. For this one, we see that they have the same difference to each one. And to get from each one, we are just going to add 4. So this one turns into 1 and 5. So in an arithmetic sequence, all these previously are sequences, okay? Whether we're adding or we're multiplying. But for an arithmetic sequence, the difference between consecutive terms is constant, and it's called the common difference. Okay? So let's tell whether or not these sequences are arithmetic. All right? So we go 3, 8, 13, 18. Well, for each one, to get to the next one, right, to get from here to here, here to here, here to here, we are adding 5. And because we're adding 5 each time, yes, the sequence is arithmetic. So it's yes, and the common difference is 5. Okay. For part B, we have 6 to 9, that is plus 3. 9 to 13, that's plus 4, and then plus 4 again. So that's kind of a weird sequence, and it does not have a common difference, so it is not an arithmetic sequence. Okay. If we look at our got it problems and tell whether each sequence is arithmetic, we're going to do the same thing. We're just going to look and see if each term in the sequence is the same distance away from the previous term, or the same thing added to 8 to 15 to 22 to 30 to get the next term. And we can see that this is not, because the first difference is 7. The second difference is 7. But then the last difference is 8. So almost, but not quite. The next one is a arithmetic sequence because we can see my common differences are all 2. For part C, it is an arithmetic sequence because my common difference is all -6. And then the last one is not a common, or is not an arithmetic sequence. It has multiplication. So this would be no, and this one would be no. Okay. So a lot of stuff here. A sequence is a function whose domain is the natural numbers and whose outputs are the terms in the sequence. And whether or not it is an arithmetic sequence, that's something that we can find out. We can write a sequence using a formula, using a recursive formula first, and then we'll look at another formula in a little bit. But a recursive formula is a function rule that relates each term of the sequence after the first 2 ones to the one before it. So if I have this sequence right here, 7, 11, 15, 19, we can use the common difference of the terms of the arithmetic sequence to write a recursive formula for the sequence. My common difference here is 4. So if I look at what happens here, we're going to let n equal the term number in the sequence and let a of n equal the value of the nth term. Sometimes you see it with notation like this. Sometimes you see it with subscript. Okay? And that would indicate which term of the sequence you're talking about. Okay? So the value of term 1, a of 1 would be 7. The value of term 2 would be, the second term is going to be equal to the first term plus 4, which the first term is 7, so this would be 11. And then that's the way this formula is going to go. It's always going to take the previous term and add 4 to it. Okay? And that would get you the next value, the next value, the next value. So recursive formulas for arithmetic sequence above is a of n is equal to a times n minus 1, or a of n minus 1 plus 4. And recursive formulas are good because they help you find the next term of the sequence. They only get a little harder to use if you wanted to say find the 100th term of the sequence. So with this formula, you would have to find the 99th term. To find the 99th one, you would have to find the 98th one, and so on and so on and so on. Okay? So we do have a better formula that we'll look at in a few minutes. Okay? But first, let's write a recursive formula for the arithmetic sequence below. What is the value of the 8th term? So I have 4, so that's not so bad. Okay, and I can see that my common difference is 7 for all of them. So a of 1 would be equal to 70. The second term, a of 2, would be a of 1 plus 7, which would be 90, or sorry, which would be 70 plus 7, which is 77. And I can see that I don't have to do them all. My formula, my recursive formula would be a of n is going to be equal to a of n minus 1 plus 7. Now to find the 8th value, I'm going to need to find a of 5, a of 6, a of 7, and a of 8. Because I have 1, 2, 3, 4 right there. So 5 would be 91 plus 7, 98. 6 would be 98 plus 7, 105. 7 would be 112, which makes 8, 119. Okay? So you do have to go through all 4 of those to get up to 8. Sorry, I got a problem. Okay? So write a recursive formula for each arithmetic sequence, and what is the 9th term of each sequence. So to do this, we're going to do the same thing we did above. We're going to try to find the common difference. So my common difference here is going to be 6, and that works for all of them, which is nice. So a of 1 is equal to 3, and a of n is going to be equal to a of n minus 1 plus 6. And for recursive formulas, you're going to need to have this line right here because you need somewhere to start. Because the second part of the formula says, well, to get this term, take the 1 before it and add 6. Well, if I want to find, there's no way to find the first term with this. So recursive formulas have 2 parts, your start and how you get the next one. So you have to have both of those. Okay, and so then a of 9 would be 51. Right, so we do that by taking 21 plus 6, and plus 6 again, and then plus 6 again, and then plus 6 again. Okay, I'm not going to go through all 4 of those. I will give you the answer for you to check out. For this one right here, for part B, my common difference is 12. Okay, so a of 1 is 23, and a of n would be a of n minus 1 plus 12. And, oops, sorry about that. And a of 9 would be 119. Okay. For this one, no difference with decimals, maybe a little bit harder to see, but the common difference is 0.5. So a of 1 would be 7.3, and a of n is going to be a of n minus 1 plus 0.5, making a of 9 equal to 11.3. And finally, this one is going down. So we're going to have a negative number. It's going down by 9. So a of 1, whoops, a of 1 is going to be 97, and a of n is going to be a n minus 1 minus 9, not plus. So is a recursive formula a useful way to find the value of an arithmetic sequence? Yes, it is, provided the sequence is not too long, provided you don't want a really, really high value. 9 was not so bad. Okay, beforehand I just added 5, or I added each difference 5 times to get the next one. There is a better way to get values for these sequences if you want to find one way in the future. Okay, so you can find the value of any term of an arithmetic sequence using something called, or you're using the recursive formula. You can also write a sequence using something called an explicit formula. An explicit formula is a function rule that relates each term of a sequence to the term number. My formula is a of n is equal to the first term, a of 1, plus the term number, n minus 1, times the difference. So let's try this with this sequence right here with this guy who's buying a guitar. So an online auction works as shown below. Write an explicit formula to represent the bids as an arithmetic sequence. What is the 12th bid? So the first bid, well, let's make a little table. So here's n, and then we have a of n, the value of n. Okay? So at my first term, right, bid 1 is 200, then bid 2 is 210, then 3, 220, 4, 230. Okay? And we can see that we're going up by, each one is going up by $10. Okay? So let's write a formula for that, or let's write my explicit formula. So A of n is going to be equal to the starting number, 200, plus the term that I want. I want the 12th bid. So that would be 12 minus 1 times the common difference of 10. And even though it might look a little weird over here to put this number next to this parentheses, right, these two numbers we're going to be able to combine to get 11, and then we just want to make sure that we multiply by 10 after that. So the 12th bid, so A of 12 would be 200 plus 11 times, let's put the parentheses here, 11 times 10, which would be 310. Okay? So let's try a got it problem. Subway Pass has a starting value of $100. After one ride, the value of the pass is $98.25, two rides $96.50, three rides $94.75. So let's just double check that this is an arithmetic sequence. Okay, so first one is worth $100. Or we can call it, this gets a little bit confusing, but it starts at 100. Okay. After one ride, the value of the pass is $98.25. After two rides, it is $96.50. So if I look at the difference here, it is $175 for each one. So let's not confuse you like this. Let's write these normal 1, 2, third term, first term, second term, third term. So A of n is going to be equal to A of 1, the first term, which is why I wanted to label this as the first term, plus n minus 1 times d. So this turns into 100 plus, I wanted to find the value after 15 rides. 15 minus 1 times 175. Okay, use my calculator and I get 73.75. Okay. How many rides can be taken with the $100 pass? Okay, so at the end of this, we want to solve for that number right there, and we want to find out when the value is equal to 0. So set it equal to 0, and we still start at 100 plus n minus 1 times my difference is 175. Okay, so now my variable is right there. Let's subtract 100 from both sides. Divide out the 175. So that'd be 100. 100 divided by 1.75, which would be 57.14. Okay, equals n minus 1. Oh, I see why I made a mistake here. Okay, this is the common difference. Oh, sorry. The common difference is negative 175. Sorry about that. So when I divide this out, right, this negative, negative, this turns positive, and now this makes more sense. Okay, because it would be weird to have negative number of rides. Add 1 to both sides, and we get 58.14. So this, if you ever use the subway or if you ever use a train pass, the leftover is, sorry, you just have to refill it up again. So this is going to be term 58, but remember that would be our 50, right? We started at 1, so that would be our 57th ride. Okay? Sorry about the mistake with the negative number. All right, so you can write an explicit formula from a recursive formula and vice versa. So an arithmetic sequence is represented by the recursive formula a of n is equal to a n minus 1 plus 12. If the first term of the sequence is 19, write the explicit formula. So I know that a of 1 is 19. Each one is going to go up by 12. So I don't even need to really mess around with this too much because I know that this is going to be my common difference. So all I have to do is say that a of n is going to be equal to a of 1 plus n minus 1 times d, which is 12. And this one would be 19. So we would have a of n is going to be equal to 19 plus n minus 1 times 12. Okay? Got a problem? Okay, for these two, same thing. So we have a of n is going to be equal to the first term, 21, plus n minus 1 times the common difference, which is 2. And for the second one, part B, we have a of n is going to be equal to 2, the first term, plus n minus 1 times 7, my common difference. Okay? An arithmetic sequence is represented by the explicit formula, 32 plus n minus 1 times 22. What is the recursive formula? So now we're going to go the other way. Okay? So I know the first term is 32. So a of 1 is going to be 32. And 22 is my common difference. So a of n is going to be equal to the previous term, a of n, sorry, a of n minus 1 plus 22. And that's my recursive formula. So explicit formula lets me find anyone. Recursive formula is going to use, this is not a variable, right? Like this is a variable, the number of term. This is a specific term in the sequence. Okay. Big difference. All right, so for the last two got it problems here, we have a of n is going to be equal to a of n minus 1 plus 10. And a of 1, I need this for my recursive formula, is 76. For the second one, a of 1 is going to be 1. And to get the next term, we take the previous term and add 3. Okay. Let's wrap this up. Our lesson check. Describe the pattern in each sequence, then find the next two terms of the sequence. So for this one, we're adding 8 to each of the previous terms. And the next two are 35 and 43. This one, we're multiplying the previous one by -2 to get positive 48 and negative 96. 3 is not an arithmetic sequence because the difference here is -7, but here the first one is -8. For 4, it is, and the common difference is 9. So for 5, to write a recursive and explicit formula for the arithmetic sequence, the recursive formula is the first term is 9, and the next term is the previous term plus my common difference here, sorry, this is going to be a -2, because my common difference is -2. Okay, that's the recursive. The explicit formula says to get this term, you take the first term plus n minus 1 times -2. Okay? Or if you want, you could, of course, written the -2 first. Okay, vocabulary. Consider the following arithmetic sequence: 25, 19, 13, 7. Is the common difference 6 or -6? It is -6 because each one's going down by 6. Describe and correct the error below in finding the 10th term. So the first term is 4. The common difference is not 8, it's 6. So if we change this to a 6, then we would get 64. And can you use the explicit formula below to find the nth term of an arithmetic sequence with the first term of 1 and the common difference of d? Ooh. So you can use this if we look at this formula, right? My explicit formula normally is the first term plus n minus 1 times the common difference. And if I distribute the difference into there, I would get this expression. Okay? And that is 4-7 arithmetic sequences.